So, before continuing with chapter 2, I would like to go through an example um, to summarize and fix a few concepts that are illustrated in chapter 2 of structure and interpretation of computer programs. So, in this video, we are going through this code that, in a few words, takes as input one PNG image and applies a bunch of transformations using the approach described in chapter 2 and produces an image, let's say in Escher style. And let me go through the code and then we will see the result. So the core idea from chapter 2, or at least the core idea of chapter 2 until now, because we didn't finish the reading of chapter 2, we are approximately half the way, is that a painter is a procedure that draws something inside a frame. So basically, to a painter is given a frame and it returns an image. And with this approach, transformations such as flip, rotate, beside, below, and square limit, which is the most Escher style transformation, do not draw directly, but they produce new painters from old painters. So to do this example, we use this library that is called 2htdp/image, and look at that prefix n image, emg, which is indicating that all the functions, for all the functions of such a library, we should use the prefix img. And in this way, we, let's say, call those functions explicitly, and we avoid clashing with our own defined procedures. So before starting with all the procedures and describing the transformations, painters, and so on and so forth, we need a bit of configuration. So as a first thing, we can define the source image. In this case, this is an AI-assisted drawing that I made a few days ago. This Adele.png, okay, the face, the portrait of a girl. And after that, we can get the exact size of that image. So we can define the canvas width and the canvas height by taking the image width and image height of the source image. We also have to define a transparent canvas that is used as the base for every painter call. In this case, transparency is essential because when two painters are combined with overlay, the top layer must not hide the bottom one. So we define the transparent canvas, and we define a white background with the same dimensions as well. And basically this is an opaque white canvas that is used as the final background when calling paint. So that in the end the saved PNG has no transparency artifacts. Okay, after these configuration definitions, we can start defining the very primitives of our code, the vectors. And we define make vector that construct a two-dimensional vector by storing x and y as a pair. Then we define the selectors for the x coordinate and the y coordinate of a vector, get vector x and get vector y. In this example, I try to use names that for variables and for procedures that illustrate what the procedure is actually doing and what the procedure is representing. Because a problem that I have with the book so far is that the name of the procedures are not very, I don't know how to say that, they're not, they don't communicate, they don't talk. And so you read, so for example, if I remember correctly, in the book, the selector for the x coordinate of a vector pair was simply vec(x). And in this case, maybe straightforward the meaning of that procedure, of that selector. But as you define more and more procedures, you may want to have to use names that are very descriptive. So there are no doubts on about what that procedure is actually doing. Also because consider that using the prefix notation in Lisp scheme, things get quite messy very fast, and if you don't use descriptive names, you'll have a very hard time understanding what a piece of code is actually doing. So make vector produces a vector, and get vector x and get vector y, select respectively the x and y coordinate of a given vector. We want also to define the operations between two vectors v and w, and so we define the component-wise addition, the component-wise subtraction, and the multiplication of a vector by a scalar s, in which basically each component is multiplied by a scalar s. Okay, and we are done for the vectors. Now we can define frames, which are built upon vectors, and you'll see why very shortly. So a frame is represented by three vectors, an origin, an edge 1 and edge 2. And basically the origin is the lower left corner of the frame, edge 1 points toward the lower right corner, and edge 2 points toward the upper left corner. And we can pack the three frame vectors into a list, origin, edge 1 and edge 2, using make frame. And as we did for vectors, we define now three selectors to access the origin, the edge 1 and the edge 2 of a certain frame. Now we can continue with coordinate mapping. Here the idea is that we want to map a vector from the unit square, so 0, 1, 0, 1, into the given frame. And here the formula is very simple because it's simply the origin plus x times edge 1 plus y times edge 2. And here we define this make frame mapper that takes as input a frame and, as you can see, returns a procedure. Returns a procedure that applies exactly that formula. And here in this definition we treat edge 1 and edge 2 as basis vectors. So x and y here are fractions, not pixels, so that 0, 0 lands on the frame's origin and 1, 1 on its opposite corner, regardless of the frame's position, size, and orientation. Then we have to make and define a few procedures to do the pixel conversion. We need to take in mind that mathematical coordinates have y increasing upward, but screen coordinates have y increasing downward. So when we place images, we need to flip the y. And here we have these unit arrow screen x and unit arrow screen y with the -1 in front of -1 applied to get vector y of a vector. Now a clarification. This arrow that in some programming languages, for example C or C is the main one, is used to access an attribute of a pointer probably, or something like that, a property of a structure or probably a property of a structure. I don't remember. It's passed a lot of time since I was programming in C and C++, and I don't have all this experience. But however, what I wanted to say is that this arrow is not part of the syntax. It's not a syntactic sugar. It's not a special symbol used in Lisp or Scheme. More simply, Lisp and Scheme allows to use these symbols like the minus and the angular bracket to in procedure names, and so we can use that, and these and usually in Scheme the arrow is used to indicate that you are passing, in this case you are passing from the unit square to the screen x, and in general you pass from one thing to one another, and so the arrow serves to communicate that there is a transformation going. So we have defined this pixel conversion, and now we can start define the painter. So this painter that we are going to define uses adele.png, the image that I've shown you before, as the primitive motif. The implementation supports the following transformations: flip vertical, flip horizontal, rotate 90 degrees, rotate 180 degrees, rotate 270 degrees, beside, below, and recursive split compositions. Basically, this implementation handles all these transformations by inspecting the transformed frame and orienting the bitmap accordingly. So let's start with a few helper procedures. The first one is the pixel is used to get the pixel length of edge 1. X and Y are scaled by their own canvas dimension before taking the magnitude that is required for non-square canvases, and also correct after rotations when edge 1 is no longer purely horizontal. The same idea is applied for edge 2, that is the vertical axis of the frame, and the center of the frame is computed by applying the formula origin plus 1/2 times edge 1 plus 1/2 times edge 2. That is the center of the frame in unit square coordinates. And we also have an helper function that returns true if the frame has been rotated by 90 or 270 degrees. Because after a 90-degree rotation, edge 1 becomes vertical, and so its y magnitude exceeds its x magnitude. And we use these to decide whether to swap width and height when scaling an image. And we also define orient image to frame. Basically, we use these to choose the correct flip rotation for an image so it appears upright inside the frame. Each transformation changes the direction of edge 1 and edge 2, and we read those directions and return the matching operation. And finally, we have the common cases produced by the transformations below. A clarification on the syntax. Square brackets in cond clauses are a racket convention. Basically, square brackets and round brackets are identical to the interpreter, but square brackets on clauses and bindings visually separates them from nested function calls, which always use the round brackets. So we have a condition for the normal orientation, for the horizontal flip, for the vertical flip, and 180-degree rotation, 90-degree rotation, 270-degree rotation, and a fallback that simply returns the image. And finally, we can convert the bitmap image into a painter procedure. The returned painter, when called with a frame, produces this is wrong actually, because initially I was using these dimensions for the canvas, and then instead I decided to use the dimension of the image, of the source image. So this is actually wrong. I will correct it later. Actually, let me use this. This is not 700 times 700, but yes, it's this, and then also can correct everything. So produces a canvas of the dimension of the source image that is transparent, with the image correctly oriented and scaled to fill exactly the region described by that frame. And so we have, as you can see, the image painter returns a procedure, and here we define a bunch of procedures. So for example, this is used to rotate or flip the source image to match the frame's orientation, and this is just the pixel width and height. This is used to scale the image, and we define the center of the frame, and finally we place the scaled image centered at the frame's pixel center on top of the transparent base canvas. Remember that place image uses top left origin and screen Y, so unit screen Y flips Y. Finally, we can wrap the source image in a painter so it can be passed to any transformation. So if you remember, image painter takes as input an image, and here we are exactly doing that. We are defining a specific painter that basically returns the procedure image painter with our source image that we have defined before. Then we have the rendering, when we can and we need to define the full frame, so the canonical unit square frame with origin in 0 0, with edge 1 0, edge 1 1 0, and edge 2 0 1, so that when we pass these to the painter can fill the entire canvas width and canvas height, canvas in its entirety. And then we can also define these procedure paint that takes a painter, takes a frame, and returns a savable image with a white background. Finally, we can define the fundamental building block for all these transformations. And with painter in region, we define a new painter that draws painter inside the subframe defined by the 3 unit square corner points, origin, corner 1, and corner 2. And basically, what happens here is that this procedure build the frame mapper for a given frame. So it maps the unit square to frame pixels, then map the 3 given corners point through the mapper, build a new frame whose origin is the mapped origin. Edge 1 goes from the map origin to mapped corner 1, edge 2 goes to mapped corner 2, and finally paint the original painter inside the new subframe. And as you can see, we define the mapper, new origin, mapped corner 1, mapped corner 2, and we defined the new frame, and finally we draw the original painter inside the newly constructed subframe. And then we can also define the transformation that are built upon these that are built upon painter in region when we flip vertical. Basically, we are passing here, we are taking a frame as argument, we are passing different frames, frames oriented in different ways. So for example, in flip vertical, we are using the same painter, but we define a frame so that it is upside down. And flip horizontal, we define a frame that is left to right, and the same goes for 90 degrees rotation, 180 degrees rotation, and 270 degrees rotation. Notice that the 270 degrees rotation is obtained by applying a 90 degrees rotation over an 80 and 180 degrees rotation. And these were the transformations. Now we have the composition. So, for example, beside places painter left in the left half and painter right in the right half of the same frame, then overlay the two resulting images. Inside this definition, inside the definition of this procedure, we define the split point, we define the paint left, again by passing a given frame, and again we return a painter that draws both halves onto the transparent canvas and merges them with overlay, so that transparent pixels don't hide each other. So as you can see, lambda frame, image overlay, and we pass paint left frame and paint right frame. The same, more or less, is done for below, that place painter bottom in the bottom half and painter top in the top half. And finally, here we start to define recursive compositions. When we, in right split, for example, we recursively subdivide to the right. At depth 0, as you can see here, the procedure takes two arguments, the painter and n. N is representing the depth, and at depth 0, so when n is equal to 0, the procedure returns the painter unchanged. This is the base case. Whereas at depth n, basically the procedure places the full painter on the left, and on the right stack two copies of the n-1 level split, one above the other. And each recursive step makes the right column half as tall as the previous. And as you can see, we have the base case when n is equal to 0, that simply returns the painter. where otherwise we define this smaller by and we call again the recursively we call the right split again. Yes, because you don't see right split here explicitly, just because right split of the painter with depth -1 is renamed as smaller. So here you see below smaller, smaller, which is actually you see beside painter applied to below smaller, smaller. And the same for up split that recursively subdivide upward, and in the corner split something very similar. You can build a 2x2 arrangement that fills toward the top right corner. And the square limit where you tile the painter 4 times with 4-fold reflective symmetry. And finally we can see the examples. So we have the first example, the original, which is exactly equal to the source image. Then we have this flip vertical, where we should see the source image flipped upside down, and indeed we can see our Adele flipped upside down. Then we have beside but we also apply this flip vertical, so we should see a vertical flipped self. Yes, so we have the original image, and beside the original image we have the vertical flipped version of it. Then we have a 2-level right split, and let's see. Yes, we have 2-level of right split. We also have 2-level corner split, and finally we have the 4-fold symmetric square limit with depth 2, which is the most Escher style image that we have produced with this code, the square limit. And as you can see, this 4-fold symmetry of our Adele. So we are at the end of this video, at the end of this code. Why this example matters, and which are the core ideas from structure, from the second chapter of structure and interpretation of computer programs so far. The first one is data abstraction. So vectors, frames, and painters are each hidden behind constructor and selectors. Nothing above the abstraction boundary cares that a vector is a const pair or that a frame is a list. And swapping the representation would only touch those few lines. Then another important concept is the one of the closure property. Just to remember the definition of closure, a set of operations satisfies the closure property when combining its elements produces elements of the same set. Just as adding 2 integers gives an integer, not some new type. And here every transformation takes a painter and returns a painter. Because the type is closed under all operations, combinations nest arbitrarily deep, And square limit is just beside and below, applied to corner split, applied to right split, and all the way down. No special cases and no glue code. Then, a uniform interface replaces a proliferation of special cases. A painter is simply a procedure that takes a frame and returns an image. That single contract is what lets every transformation compose with every other one without any of them knowing about the others. And finally, stratified design, because the system is built in clean layers, arithmetic on vectors that are used to define frames and frame coordinate mapping. Then that is used to scale the bitmap, that is used to apply geometric transformations, that is finally used to do recursive compositions. Basically, each layer speaks only to the one directly below it, and complexity is managed by never letting a layer leak its internals upwards. So I think these are the main takeaways from this chapter 2 so far. This is a cool example, and I think I'm done for this video. I will continue reading chapter 2 in the next one. So, ciao ciao!